All right, class. Today we're going to finish up Chapter 18 on thermodynamics, specifically Gibbs Free Energy. And I think the main thing about this lecture is we're going to talk about different equations of Gibbs Free Energy, and each one has their purpose. And so you have to, through reading the problem, decide which Gibbs Free Energy equation you need. And what it depends upon is what information do you know. So this first equation on this slide is similar to, again, delta H of reaction, standard enthalpy of reaction that we did in Chem 170. And here, the only way you can use this equation is if you know the Gibbs free energy formations of the products in the reactant. So that has to be gained from a table or an appendix. And you don't always have that available. So the next equation in the middle there is what we've been talking about, which is the change in Gibbs free energy. Standard Gibbs free energy is equal to the standard enthalpy of the reaction minus the temperature in Kelvin times the entropy change, standard entropy change of the reaction. And sometimes that's given in the problem, like the temperature at which the reaction occurred, and then they tell you what the delta H was and what the delta S is. Sometimes they just give you the equation, and you will have to go into a table and calculate delta H that we learned previously in Chem 170, which looks pretty much like the top equation. Instead of delta G, you have delta H here. So you may want to look at that just to get an idea, but don't just give up on a problem, because it really does come down to, is it a direct method where you have to look at tables and get enthalpies and entropies, or do they give you the enthalpy changes and the entropy changes? So you're going to have to read the problem and decide the path that you're going to use to solve the problem. But let me just say, all these problems are solvable. So once you read the problem, you should be able to formulate which way you're going to go to solve the problem. All right, so let's look at a problem here. So this is 18.6, and it says calculating the standard change in Gibbs and free energy for a reaction using. So they're being nice to you. They're telling you what equation that you're going to use, okay? And it says one possible initial step in the formation of acid rain is the oxidation of sulfur dioxide to sulfur trioxide by the reaction. Calculate the standard Gibbs free energy of the reaction at 25 degrees Celsius and determine whether the reaction is spontaneous. All right. So what we know is this. If it's spontaneous, delta G, standard Gibbs free energy for the reaction, has to be a negative value. If it's not negative, it will not be spontaneous in the forward direction. So you're looking at this problem and you're going, well, shoot, this problem's unsolvable. I don't know what delta H is for this reaction. I don't know what delta S is for this reaction. The only thing I know is that it occurs at 25 degrees Celsius. Well, that has to be converted to Kelvin, and there's the temperature in bold here. So we definitely have the temperature, but if that's all we had, that'd be one unknown out of three, and we couldn't solve this problem. So what does that tell you to do? Well, that tells you that you're going to have to calculate delta H and delta S by looking at a table in the appendix. So this is what it looks like. Make sure you can access this appendix 2B. And again, if you had a problem on a test, you would have something like this where it would be integrated into the problem itself. But let's look at this. So sulfur dioxide gas has a standard enthalpy of formation. Notice that's in kilojoules per mole of negative 296.8. So what does that mean? It means when sulfur dioxide is created by 1 mole of sulfur and 1 mole of diatomic oxygen gas, that it would release 296.8 kilojoules per mole of energy. So it's exothermic. Now, you're looking below it at oxygen, and you notice that the standard enthalpy of formation for oxygen is 0. Well, we've talked about this before, is that I cannot tell you how much energy is in something until I change it. And so we can only measure changes in enthalpy, changes in entropy, and it's really the same thing with delta G. We can only measure changes in Gibbs free energy. So the standard definition is any element that's in its standard state at 25 degrees Celsius, 1 atmosphere pressure, is going to have a standard enthalpy of formation of 0. So that's why oxygen is 0. But then you look at the entropy and you go, wow, it's got a 205.2, positive 205.2 entropy. Well, let's think a couple of things. First of all, this isn't kilojoules. This is joules per mole, Kelvin. And so we also know, by definition, third law of thermodynamics, that the only thing that has 0 entropy is a perfect crystalline solid at 0 Kelvin. Well, oxygen is a gas. It's 2 oxygen bound together, so that gives it a little bit more, it can translationally move and so forth, or rotate. And so, yeah, it has a fairly high entropy there. Sulfur trioxide, not a pure substance. And I mean, not a, I don't want to say not a pure substance, because it is. It's a compound. But it's not an element. It's not an element. So it definitely has a standard enthalpy of formation, and it also has a entropy. And I notice that entropy is a little more than oxygen, and it should be. Why? It's more massive, and it's got a little bit more complex geometry than diatomic oxygen. So we use this information from the table to calculate standard enthalpy of reaction, and we'll also use this table to calculate the standard entropy of the reaction. So think about it, write that down before you advance. So maybe hit pause and see if you can calculate standard enthalpy of reaction for this, and for sulfur dioxide reacting with oxygen, and standard entropy of the reaction. If you can do that and you get the right answer, then you're on the right track. These are easier problems. These are easier problems than what we've been doing. This is just basic math. So here's what they look like. This is called the direct method, again, of calculating the standard enthalpy of the reaction. It's the summation, number of moles, of the standard enthalpy of formation of the products, final minus initial, so that's why it's products minus reactants. And you say, what are these standard enthalpy of formations? Again, they're found in the back of the book in a table. And that's how much energy is required or released when a particular substance is made. So we look up the standard enthalpy of formation of sulfur trioxide. That is our only product. So there it is in brackets. Minus the standard enthalpy of formation of sulfur dioxide. Plus the mole in front of the oxygen is 1/2, so we say 1/2 times the standard enthalpy of formation of oxygen. You say, why'd they do that? Well, to be complete, that's correct, but you know the standard enthalpy of formation of a pure element in its standard state is 0, so there it is, right below, 0 kilojoules. Here's negative 296.8 for the sulfur dioxide standard enthalpy of formation. And like I said, make sure you solve in the brackets first. And so you would get negative 395.7 minus a negative 296.8. Minus a negative makes that a positive. And so we get our total here, our standard enthalpy of this reaction is negative 98.9 kilojoules. So not hard, very straightforward. Just be organized and pull the information from the table. The most common mistake, again, is students don't fill in calculate what's in the brackets first. They try to hurry it and just say this minus this, and then they forget to subtract this one, really. So that's why you got to do the bracket. Doesn't hurt you here because oxygen is 0, but that's one thing I see. The other thing I see in this problem is students don't watch their units. You've got to watch your units because that's going to become important, especially when we plug it into the Gibbs free energy equation. All right, so you got half of it done. Now you got to calculate the standard entropy of the reaction. So you may want to pause, solve for that. All right. So this is what it looks like, standard entropy of the reaction. And again, same thing, summation, number of moles of the entropies of the products minus the summation, number of moles of the entropies of the reactants. Notice that doesn't say delta H. And the reason why it doesn't say delta H is because, delta S is because we know what zero entropy is. So we have a specific value for entropies of substances. So we plug these in, and again, here's where you do make the mistake. So this is what I see students do who try to rush this, and they don't solve what's in the brackets. They would say 256.8 minus 248.2 plus 1/2 of 205.2. It's not plus this. Remember, it's subtracting everything within the bracket. So solve for what's in the bracket, and then say 256.8 minus whatever this summation is in the bracket, and you won't make a common mistake. So the next common mistake is that when you calculate this out, you get negative 94.0 joules per Kelvin, and that unit at this point could not be added or subtracted from just kilojoules. Remember, units have to be the same before you add or subtract them. So that Kelvin's easy to fix because Kelvin, it's at 25 degrees Celsius. We change that to 298. And what they did was change the kilojoules to joules. And that's fine. That's the easy way because what does K stand for? 10 to the third. So they just keep it in joules. I think that is okay. And then they subtract the T delta S from the enthalpy, and they get a negative 70.9 10 to the third joules. Let me just say, anytime you're calculating delta G, you almost always put it in kilojoules. So if you use joules up here, you'll eventually have to convert it to kilojoules. Now this is an easy one because it says 10 to the third joules, and you know kilo means 10 to the third, so it's negative 70.9 kilojoules. So you go, why do I need to do these calculations? Well, it tells you that Gibbs free energy is a negative 70.9. So this reaction at 25 degrees Celsius will be spontaneous. It will happen. All right? Doesn't tell us how fast, but it does say the conditions are favorable for this reaction to proceed in a forward direction. And that's what contributes to acid rain. Sulfur dioxide mixes with oxygen in the air, and it is favorable at room temperature, and that forms sulfur trioxides, and sulfur trioxides react with water and form sulfuric acid, and there's our acid rain, or a component of. All right, good question, easy, but again, methodical, very long. You've got to, again, first thing to do is establish which delta G equation you need. They're nice to you on this one because I tell you what it is. Delta G equals delta H minus T delta S. And then you don't have anything but the temperature to begin with, so you'd say, well, this is unsolvable unless I can calculate enthalpy and entropy. And you say, well, yeah, those are in the standards are in the table, all right? So that tells you that you have to use the direct method to calculate the standard enthalpy of the reaction and the standard entropy of the reaction. All right, so let's look at this problem. Estimating the standard change in free energy for a reaction at a temperature other than 25 degrees Celsius. So the one we just did, that was at 25 degrees Celsius, and now we're going to say at 125. Is this reaction more or less spontaneous at an elevated temperature? All right. Let's go back. Let's go. Well, we can go forward here. All right. So here is what you know. So delta H for this reaction. This is the way you want to think about this reaction. Delta H is exothermic, okay, and that gives off heat. But entropy is less entropy. We got a negative value for the entropy change. And what did we say? When delta H is negative and delta S is negative, then temperature comes into play. And this is what you got to remember. If delta H is negative and entropy is negative, when does this reaction become spontaneous? At high temperatures or low temperatures? And if you can't answer that, then you haven't spent enough time on that table that talks about delta G values, spontaneity, and delta H and delta S values. You have to know that table. Now, it's easy to figure out. So here's what you know, is that delta H is negative, delta S is negative, and then we have minus T delta S. So the higher the temperature becomes, the more the T delta S term is going to dominate, and then that will give us a delta G that is positive, because a negative time, subtracting a negative number makes it a positive, right? So you want the T delta S term to be small, and you want the delta H, which is negative, to dominate, to keep delta G negative, which means it's spontaneous. So if you raise the temperature, it's not going to be as spontaneous, because at 25 degrees Celsius it is negative 70.9 kilojoules. At 125 degrees Celsius, it's negative 61.5, which makes sense. When both the delta H and delta S are negative, you want the delta H term to dominate in the reaction to make delta G negative. In this case, we raise the temperature. The T delta S term dominates more than what it did previously at 25 degrees Celsius, and the overall delta G of the reaction is less. That's what you want to get out of the heart of these problems, is to be able to think of it theoretically, but also show the calculation. Good question. That was a good one. Makes you kind of integrate about 3 different concepts that we've covered together. All right. Standard Gibbs free energy. The change in free energy when 1 mole of compound forms from its constituent elements at standard states. Looks exactly like standard enthalpy of formation, again from Chem 170. When we did this in Chem 170, we called this the direct method. The direct method, if you want to know the standard Gibbs free energy of the reaction, it is equal to the summation, number of moles, of standard enthalpy of formations of the products, minus the summation, number of moles, standard enthalpy, Gibbs free energy of formation of the reactants. I don't know if I said Gibbs free energy here or not. Standard number of moles, standard Gibbs free energy of formation of products, minus summation, number of moles, standard Gibbs free energy of the reactants. So again, energy, we don't have a 0 point. We have to arbitrarily set that. And so we say again, just like with delta H, any element in its standard state has a Gibbs free energy of formation, standard Gibbs free energy of formation of 0. So that's what you're seeing in this table. Hydrogen, oxygen, nitrogen, carbon, graphite naturally occur as elements, as these elements in these phases at 25 degrees Celsius. So that's why their standard Gibbs free energy of formations are equal to 0. That would be the same thing for the delta H of formations, the standard enthalpy of formations. They would also equal 0 as well. So that's what you got to remember, is that energy, we have to have a reference point, and we have defined a reference point to do these calculations. All right, so ozone in the lower atmosphere is a pollutant that can be formed by the following reaction involving the oxidation of unburned hydrocarbons. Use the standard free energies of formation. So what I want you to get out of this problem is they don't talk about delta H. They don't talk about delta S. They want you to calculate this using the standard free energies of formation. So that means table. That means you have to look in the table to solve for this. Now, it's the same process that we use for calculating the standard enthalpy of a reaction, or standard entropy of the reaction. First thing you do is you look at all of the substances and look up their standard Gibbs free energy of formations in the table. Now, once you get good at these, you don't worry about the oxygen. You know that's its standard state, so it has a Gibbs free energy, a standard Gibbs free energy of formation of 0. But the rest of these are not elements, they're compounds, except ozone is an allotrope, but that's not its standard state, so that's why it's 163.2. All right, so what do? Products minus reactants. Real easy. So here it is. The standard Gibbs free energy of the reaction is equal to the summation, number of moles, standard Gibbs free energy of formation of the products, minus summation, number of moles, the standard Gibbs free energy of formation for the reactants. Plug in what you know inside the brackets for the products. Plug in what you know inside the brackets for the reactants. Total the values in both these brackets. So here's what we get, negative 98.8 kilojoules. We get 50.5 kilojoules here because it's minus a minus. So let's see, does that look right? Let's see. Yeah, negative minus a minus makes that a positive 50.5 kilojoules. All right. We add these two things together, we get negative 148.3 kilojoules. So what you should know at this point is this reaction is spontaneous. It's a spontaneous reaction because delta G of the standard Gibbs free energy of this reaction is negative. So we know it's a spontaneous reaction. All right, here's another problem. Try that one out. More. All right, so now let's talk about the relationship between delta G values. Okay. Notice we're not talking about standard delta G values. We're just saying delta G values. So delta G is a state function. That means you define it at a particular point in time. If the reaction is reversed, the sign of delta G reverses just like delta H. If it's exothermic negative 100 degrees in the forward direction, the reverse reaction is a positive 100. So same thing with delta G. Same thing that we learned before, that if you multiply the entire equation by a multiplier, you also multiply the delta G just like you did delta H. Let me give you an example of that. Okay. So if you had, here's a classic one we did when we were talking about delta G. We said 2 moles of hydrogen gas react with 1 mole of oxygen gas, and that forms 2 moles of water, liquid. All right, so this reaction is balanced. Well, if we wanted to say 4 moles of hydrogen gas reacts with, or I'll do it this way since I've already started. 2 moles of oxygen gas yields 4 moles of water. Whatever this delta G of reaction is, standard Gibbs free energy of reaction is, this one is 2 times that. So this would be 2 times the delta G of the reaction of the first one there. So it'd be 2 times this, because that's the multiplier. So we've seen these before when we did delta H, and those are a couple of tools that you need to know. And then the other tool that you need to know is that if I reverse the reaction and say 2 moles of water, liquid, and you got to make sure you put the phases in, because if you don't do that, it can throw you off, your answer off. So that looks kind of sloppy, but that's the way it is. So that would have the reverse. That's the reverse reaction, and that would have just the opposite sign of the forward reaction. All right. So again, it's really a Chem 170 thing. This was called Hess's law. All right. So in Hess's law, what you do is this is called the indirect method. So in this problem, you have 3 equations that you know the delta G of the reaction. So notice here, you're not using the table in the back of the book to do a calculation called the direct method. They give you specific reactions. You're going to combine these 3 reactions to end up with this reaction here. So think of it like a puzzle. How are you going to manipulate reactions 1, 2, and 3, so that when you add them together, you get the final equation that we see up here. Now, if you had this in Chem 170, I bet you remember it. It was that important. It was at the very end of the semester, though. A lot of people are tired. But let me show you how this works. So the first thing I would focus on is I would look at that carbon. And so that carbon, there's 3 moles of carbon, and I would look at all these equations, 1, 2, and 3, and do I see any equation that has carbon solid in it? Well, the only equation that has carbon solid in it is equation number 2. And the other thing I know is that I got to have 3 moles of carbon, so the multiplier here is going to be 3. So that means I'm not changing the sign. We're just going to multiply that equation by 3. All right, so we multiplied, it went away, didn't it? Multiply that equation by 3. Now, let's look at hydrogen. Well, the only equation that has hydrogen in it is equation number 3, and it's on the side we want it on. The hydrogen is on the reactant side up here, and it's on the reactant side here. So that tells me I'm not flipping this equation. I'm going to leave it as is. And it tells me that I need to multiply this entire equation by 2. And I'm going to put the 2 here so it doesn't conflict with the 3. So that tells me I'm going to multiply that one by 2. Now, the last equation, we saved it for last. We see that the propane is on the product side. Here, it's on the reactant side in equation 1. But it is the right number of moles. So we're going to flip this equation. And by flipping it, it changes the sign to a positive 2,074 kilojoules. All right? So we flip the sign, we flip the equation, and now we're ready to add them together. So watch how this works. All right? So they flip the first one, change the sign. Now we have the propane on the proper side of the final equation. For the second equation, we multiply by 3. That's what we said. Multiply by 3. And we get negative 1,183 kilojoules. Third equation, we said multiply by 2. Now, I think it's important to do this. You write all 3 equations after you've manipulated them. You write all 3 equations down. And remember how this works. Anything on both sides of the chemical yield sign, one's going to subtract from the other. So here you have 4 moles of water on the numerator side. I mean on the reactant side. And on the product side you have 4 moles of water. So they cancel each other out completely. Let's look at the oxygen. You got 3 and 2 moles, total of 5 moles of oxygen on the reactant side. You got 5 moles on the product side. They cancel out each other out completely. And you have 3 moles of carbon dioxide on the reactant side, 3 moles of carbon dioxide on the product side. They cancel each other out. So what's left standing? Well, you bring that down. 3 moles of carbon, 4 moles of hydrogen yields propane. You add up your numbers after the manipulations and you find out that the delta G of this reaction is negative 23 kilojoules. So this reaction is spontaneous at this temperature. It's not, it's not great, but it is spontaneous. So this is called, we did this exact same process in Chem 170 when we did Hess's law indirect method. And what that is saying is that maybe this reaction directly is too fast to measure. Maybe it's explosive or something like that. So what we do is we do reactions that we can control, that are slower, that we can measure how much heat's absorbed or lost. And then we combine these equations. And because delta G is a state function, it doesn't matter. It's pathway independent. It doesn't matter whether we do it in a direct step or in multiple steps. You still get from here's point A, here's point B, and as far as the energy goes, it's the difference between here and here. All right? So it doesn't matter whether I zigzag up like this or I go directly up like that. My energy, now we're not talking about how much work's done and so forth, but my energy is a state function. So that's why we would do the indirect method, is we have to have a way to sometimes measure things indirectly because they're too fast or too hard to measure. Good equation. All right, there's another example. All right, so the thing about free energy is, and this is important, this is where it gets into the real world stuff. This is for those of you who want to be engineers, this is the important stuff right here for engineering. This is your first introduction of free energy and what it means to an engineer. So free energy is the amount of energy released from a system that is available to do work. In fact, that's the definition of work. The ability to, or the definition of energy is the ability to do work. So, and specifically, it's the ability of the system to do work on the surroundings. All right? So for exothermic reactions, like the combustion of an engine, combustion of gasoline in an engine, some of the heat released as a result of the enthalpy change goes into increasing the entropy of the surroundings. Makes sense, right? When we combust the gasoline in the car, we have heat coming out of the exhaust, and that's going to make the molecules more energetic, and so the entropy of the surroundings is going to increase. So what this is saying is some of the heat released as a result of enthalpy change goes into increasing the entropy of the surroundings, so it is not available to do work. All right, so some of that is lost to entropy. All right, even some free energy is generally lost to heating up the surroundings. So we got that too, okay? So here's an example of carbon, graphite reacting with hydrogen to form methane. It's a exothermic reaction. It's a negative entropy change because we went from 2 moles of gas to only 1 mole of gas, so it's unfavorable. And the delta G of the reaction is negative 50.5. It's spontaneous. So again, negative delta G says it is spontaneous, and maybe we'll get some work out of it. But delta G is less than delta H because some of the heat released is lost to the entropy in the surroundings. So that's what they're showing here is the difference between negative 74.6 and negative 50.5. Some of the heat is lost to this unfavorable entropy change. So we don't get as much work as we would hope out of it. This is why, you say, why do I need to know this? This is where you want to be a proponent of using solar panels to power your house electrically. This is one of those big arguments that a lot of people make about electric lines versus solar power. A lot of the energy, the work that's in the electrical lines is lost due to heat. You don't have those long lines when you have a solar panel on top of the house. And so that's an argument that we're burning a lot of fossil fuels or nuclear energy to get this power to everybody's house and put it on a grid just to see it lost in the form of heat. All right, so here's another one. The change in free energy is a theoretical limit. Everything we've been doing is theoretical. If the reaction achieves a theoretical limit, it is a reversible reaction. So what that means is this gas pushes the sand up, so the gas is doing work on the surroundings, and it pushes it up even more, because we took some of the sand off. So as we take the sand off, the gas pushes against, we see that sand rise there. This is a reversible process. We add more sand. We would expect if we went in reverse that if we added more sand, yes, the gas would be compressed. Tell me, though, what you notice about this reaction. Like, can you look at this and tell me why it's reversible versus maybe the previous reaction? What makes it reversible? It's reversible. I mean, if you did this in the lab, if you took sand off the platform, yes, it would expand. If you added sand, but it's reversible. Well, what you notice is we're not losing any heat. We're not losing any heat. So once we start losing heat, then the reaction becomes irreversible. So here's your electrical one. You got the battery, it goes to the motor, it cranks up the starter, does some work, and then it goes back. Every time that current flows, though, some of the energy is lost as heat. And so that makes this reaction irreversible. We're not getting, and we're not talking about what's inside the battery in the reversible process here. We're talking about the process. And because this process loses heat, this reaction is irreversible. Oops. All right. I think we'll stop here. I think I'll just make a third video. I think this is a good place to stop. The next thing we want to talk about is Gibbs free energy changes in non-standard conditions. And we also want to talk about the relationship between Gibbs free energy and equilibrium. And I think that's another fairly long video. It's not like the first one, and it may be, hopefully it's about the same length as this one or shorter, but I think this is a good place to stop for today. Again, if you have questions, email me. I'll be glad to answer them. Thank you.